Vietnamese.
Yeah.
And your nationality?
People from UAE call
Egyptian.
So maybe they don't like Egyptians in this donut shop. I don't know. Maybe they only want Vietnamese customers. Maybe it's a type of donut racism. I don't know. Where's this place?
It's next to Slim College Green.
What's it called?
Boston Donuts.
What?
You
Yeah.
bought donuts for two?
2 donuts for 3, and he bought 1 donut for 1.
2 donuts.
2
Oh.
donuts should have been 2. Like 1 for
Unless you bought the expensive donuts.
Yeah, they have different prices for different donuts.
Hang on. We'll easily solve this. What flavour did you get?
I got an Oreo, and the other one was like strawberry, I guess.
And what did he get?
He got the strawberry one.
And?
The Oreo.
So the Oreo is more, yeah, the Oreo.
So the Oreo, yeah. Oreo's fancy here.
When here donuts are expensive.
Yeah, bro.
Like we buy it from half the price.
But it's worth it.
It is worth it. They're delicious.
I like Dunkin' Donuts and Krispy Kreme.
Dunkin' Donuts, you make me sick. Right. How American, Dunkin' Donuts.
That's what we have.
Sounds terrible. Physics now? No homework? Start next lesson?
Yeah.
That's all you just know? Now we have everybody.
I hate you.
If I give you half back, you have to write half of it. Your choices are the first half, the last half, or every second letter. S-E-I-I-H. You can do it this way too if you want. Okay, you have that?
For €3.
Oh my goodness, we know. Okay, we know.
Tesco.
Let's go, yeah. Okay.
Please. No Tesco advertisement, okay? My YouTube channel is ad free, alright?
I felt bad I didn't buy 6 more. It's so nice.
This is what you're going to eat for the rest of the week, is it? Right, did you write this down? Oh, come on.
Also from Tesco you can buy a sandwich.
I know.
Yes, or
I know, for
yogurt and a
$3.50.
drink for
Yes,
$3.50.
yes, I know.
So nice.
No.
How was the naked noodles you had the other day?
They're delicious.
The duck ones.
Yes, poison duck is good.
They're shameless as
No,
well.
no more advertisement. Okay.
Very bad.
Right. So, why does metal feel colder than plastic? Or, well, what's it?
Less heat capacity.
Yeah, well, I mean, why would
Like,
a piece of metal at 10 Celsius feel colder than a piece of wood at 10 Celsius? If they're both at 10 Celsius. Why does it feel colder to your hand?
They don't have the same internal energy.
yeah, but why?
Yeah, yeah.
Metals conduct heat
Less thermal.
Which, how does that affect?
It's like it even lets the heat out easier.
Yeah, yeah. Who's calling me? I don't know who this person is.
Okay, you can understand.
I think it is important. Hello?
What did you guys do?
Nothing.
Really?
Yeah.
Honestly, you should guys try going on the
Why?
3 hours break. Because you feel so fresh after.
No, I don't want it with someone.
Because you're exercising.
Just pass it along.
Waking up.
I can tell like this.
You just
No, don't do it.
Just take it.
After the gym,
No, I went to the gym and I took a shower and I ate.
then your foot up.
Everyone. I mean, like after the gym.
That was confirming my internet. Right. So did anyone give me the answer? No, you were saying it because you weren't right. Yeah, and why does that make it feel colder? You have the right answer.
Because it lets it takes in heat faster and lets heat.
That's exactly it. For the same reason, why does water at 10 feel colder than air at 1? The same reason. So my point is, temperature is not enough. We need another way to talk about heat and temperature. Metals will feel hotter sooner than plastics when you heat them. In fact, conductors will feel hotter than plastics when given the same amount of heat energy. In other words, conductors get hot quicker than plastics. Some materials warm up faster than others. Why is this? Different materials have different capabilities when it comes to absorbing heat energy and increasing their temperature. So some materials just take the heat quicker than others. Okay? So conductors take the heat quickly, insulators slowly. Yeah?
Question.
Yes.
Is it because they have more free electrons?
We'll get to that soon. So we have this term called specific heat capacity of a material. And basically it's the amount of energy you need to increase a unit mass by a unit of temperature. So for example, it's the energy you would need to increase 1 kilogram by 1 degree Kelvin. This is a typical definition asked for in the exam, so please write this down.
Is it the same as lasting heat capacity?
No. Little is a hidden heat.
If A was the same as B, then B would be called A as well.
Otherwise,
In my O-level physics textbook, I had two definitions, one for specific heat capacity and one for heat capacity.
yeah.
And it was
Interesting.
like, it was too explain.
Yeah. I don't know where.
What was the difference?
They just removed the 1 unit of, it used to say like per kilogram, I think, like the amount of energy required to raise 1 unit of mass. 1 unit, instead of 1 unit, it had 1 kilogram of mass by 1 degree Celsius.
That is
That's
stupid.
The specific. The other one didn't have like 1 kilogram. Raise a body by unit of Celsius.
Strange, because I've never seen that distinction in physics books before. Here at least, or at least in the exam, which is what you care about, it's just specific heat capacity. Okay, did you write that definition down? Some people have seen it before. Yeah. 1. Yeah, that's okay. So,
Keep it.
can you just spend 1 second here calculating the units of this term? What's the units here? Anybody except Faisal. So give me the units.
kg per
No? Say again? Joule per? Yeah, or per Kelvin. Joule per kilogram Kelvin.
Yes, it is kg. Joule.
You started off with kg. You start off with J. Joules per.
Kilogram.
Okay. So, if you think about the definition and the units used, you can arrive at this formula for energy. The energy required to increase m kilograms by delta theta of temperature is just mc delta theta. So in other words, if you want to know how much heat energy you need, then you just need to know the mass, the specific heat capacity of the material, and how much extra temperature you want. And that's all. Sorry, I'm going to fix my pen.
That's nice, isn't it?
Tasty.
Yeah. 20 watts for €3.
You really hit the jackpot moving to Ireland.
I feel so happy when I buy from those discounts.
Me too. My favourite is to go to the section where the food is nearly expired.
Yeah, I was looking, I was like, why is this so cheap? So yeah, it must be expiring soon. Then I was like, 29th of March. I'm like, what? It's expired already? 2018!
Jackpot.
Even if it was 2017, I still bought it.
I think it depends on what it is. Some foods are perfectly fine after their date. Things like meat and dairy.
Bread
And bread, definitely.
turns green.
Pretty quick as well. You got this? Yeah. Okay. So here are some values of different materials. First one we'll do is water. The most famous one of them all. Roughly 4,200.
Is there anything that to give it energy will cool down? Or such materials do not exist?
If you give it energy,
It cools down.
I feel like that would violate the second law we were discussing last time. That if you put energy in...
Rules were made to be broken.
Oh, true. I do not know of any material right now that cools down as you put energy into it. I doubt that one exists or is even possible to exist.
But like, for example, if there are two chemicals and you give them energy, then it's an endothermic reaction. Then it will cool down.
Yes, but you're spending energy to cool it down because of the change in the bonds or whatever magic chemistry happens. So not quite. Nearly. Keep thinking about it. If anything weird is going to happen, it's going to have to be quantum. Okay. Liquid
It's
water.
such an interesting part of physics, but it's so difficult.
You have no idea how difficult it is.
We're gonna do it.
I tried, then I gave up.
3 courses on it actually. I
Of
did.
the electric effect?
Are we gonna do it?
A
Yeah.
tiny, like 1 page of it. Yeah.
Is it the photoelectric?
Yes, and something else too. Liquid water. Now, what this is saying is, if you have 1 kilogram of water and you want to increase it by 1 degree, how much energy do you need?
4,400.
Nearly 4,200 joules. That's a lot for just 1 extra degree.
1 kilogram of water.
1 kilogram, which is a litre.
Yeah.
Ice, interestingly, although it's still water, it only needs half the amount of energy to increase in temperature. Which is interesting because you think it should be the same,
No, more.
or more even, but in fact it's half.
Is it because of the change in the volume?
This change in the state, I think, yeah. Next is steam, which is about the same as ice, interestingly.
Yeah, liquids. Is it true that liquids have the highest specific heat capacity?
Probably is true for most situations, although there might be some exceptions. I think it should be the highest, yeah. Next,
Doesn't it depend on how tightly the molecules are packed?
we'll get to the reason why shortly. I'll keep you in suspense until then. Okay, copper.
Lower.
It's very small compared to water. This means you need only 385 joules to increase a kilogram of copper by 1 degree. So you don't need much. Milk. Why not, I thought. 2,850. Alcohol, also 2,300. Lead, a measly 129. which means lead will get very warm very quickly. It'll do anything with it really. It's like if you hit it against the wall hard enough, it'll warm up. You only need to put 129 joules of energy into lead and it will warm up by 1 degree.
Does this apply to the gases? Which cases?
Oh, all of these are solids except if I tell you otherwise. Oh, well, no, milk. Milk. Oh, yeah, sorry, what am I saying? No, these would be like at room temperature, solid.
Yeah, that's what I'm thinking. If ice
Liquid,
was kept
liquid.
in room temperature, then it will tend to increase its temperature if it's in room temperature. But like if we do this experiment at 0 degrees, will water have the same and will ice have the same? I wanted to ask this.
Oh, good question. If it's at 0 degrees, would water and ice have the same?
Yeah.
No.
Because if we're doing this at room
It's not
temperature,
because the temperature of the room or anything like that, it's because of the state it's in. So water at 0 and ice at 0 have different heat capacities because of their states. Next one is air, which is big enough, 1,000 joules per kilogram of air.
How's air less than water?
yeah,
How's air less than water?
You need more energy.
less,
Less
if
energy.
it's
It's easier to heat up air than it is water. 4 times easier, in fact. So if you had 4,000 joules, you could use that 4,000 joules to heat up water by 1 degree or air by 4 degrees. So you can heat up air 4 times faster than water.
Is it the same concept as how long it takes to lose its temperature? Like I'm thinking of it if we
Not necessarily.
water and air.
Mm.
Water will stay colder more than air for a longer period of time.
That is related to this, yeah. Now, why do materials have different heat capacities? This is what the two of you were asking. Just before I go on, I do want to say, what's the highest one there? Water. And it turns out that's really important in biology, that water has such a high heat capacity, because you know that
the body.
yeah, you are all mostly made of water. So it means we all have high heat capacities, which means it's difficult to change our temperatures because you need more energy, which is good because we like being at the same temperature. So although it might be warm or cold outside in Saudi Arabia or Ireland, whatever, very different countries, your body temperature is actually still the same, yeah. Yeah, and part of the reason your body's able to do this is because it's mostly made of water. Yeah. So, why do materials have different heat capacities? Why does lead have such a small value and water have such a high value? Well, the answer is, you'll be disappointed. It's complicated. And we might look at it later, but we probably won't.
You just have to do the.
I was waiting to do that.
Yeah, that's a bit
I-
suspense.
Yep.
If
But
you up very high,
yeah.
it'll crush you down.
It would be no fun otherwise.
Take it to the
Yeah.
desert and left your back.
That's it. In fact, there is no. I looked this up before, and there isn't any easy answer. It's because of blank.
So it's not the way the material is packed.
No, I never said that.
It doesn't have anything to do with that.
I never said that either.
Wow.
It could be, but that could just be one of many factors. So, like I said, complicated. Okay. Huh? Better that you don't really know, is it? Okay. Continue? Yeah? Okay. So, here's a question that we'll do together. How long would it take to boil enough water to make a cup of tea? By using a small 1 kilowatt travel electric kettle. And we should estimate the initial temperature of water and all that other stuff too. So we'll do this one together.
We need the amount.
Yeah, we'll estimate everything. So, we have our kettle. And the power of the kettle is 1000 watts. How much water do we need for making a cup of tea?
100 milliliters.
That is a pathetic cup of tea. 200? That's nothing.
Yeah, how much
This
is
is
this?
100. No, too small.
This is not 100, this is 500.
That's 330.
No, less than 500.
It's 150.
Impossible.
300.
I'd say this is 250, but this is a small, pathetic cup of tea. No, a good cup of tea.
Yeah, we drink teas with those.
500.
A good Western cup of tea.
Yeah.
A liter.
I'd say about I'd say about 0.25, we'll say.
250.
Roughly.
Yeah.
Yeah. Now, when the water comes out the tap, what temperature would it be at when you put it in cold?
Fine.
Now remember, this is an Irish tap of water. 15 on a warm day, maybe, yeah. We'll say 15. At what temperature are we trying to get it to?
100.
100. So, what's the increase in temperature? 85. So the formula for the energy is mc delta theta. That is 0.25 times 4181 times 85. What's that, please?
What's the Q again? The heat.
It's the heat required, the heat energy.
Energy required, and then mass, then the specific capacity, and the change in temperature.
8, 4 seconds.
Now I said time, didn't I? I want to know how long. So power equals work over time. Time equals work over power. The work required here is 88846 joules. And what's the power, did we say, of the kettle? 1000. So this will take 88.8 seconds, which is 1 minute, about 1.5 minutes practically. About 1.5 minutes. Okay, simple example to start. Can you write this one down? Did you write this down? Go back to sleep.
That's because they didn't oxygen.
Did you write this down?
What's the answer? The answer for the second one, you just asked it.
No, what I was asking was, we all agreed Lee should buy us frappuccinos.
Yeah.
Yes. Yes.
Maybe stronger ones.
Double espresso. There is no question on this, Faisal. The cake is a lie. Okay.
You missed all the cake on sports day.
Oh, who won the cake prize?
I don't know.
I'm
We
not
just
very
ate.
sure.
Good enough.
But I have pictures of the teachers eating it like.
Just
It's kind of weird. But you're kind of weird, so it's all
And
balanced.
I learned how to play the...
Hurling.
Yeah.
Yeah.
Yes, I heard you were quite good at it actually.
Leo was good. Leo broke the thing like a million times.
I got
You got the link from Miss email?
Possibly. I don't read all my mails. Okay.
Right now.
You wrote this down? Yes? Okay. Now I'll look at it later, Faisal. Right. We'll do this one together as well, but I want you to try it first. Please remember that you're looking at the capacity for ice, which is different to water. It should only take you a minute, really. Can you try it?
Temperature has to be in Kelvin.
No.
No,
Because
no,
of the change
it
in
should be, but for this lesson we don't need it to be.
If the temperature changes by 5 degrees in Celsius, then it's also changing by 5 degrees in Kelvin. So it doesn't matter.
Got this? Got that? Do we have an answer, guys? Yeah.
This is 1.8 kilo
joules.
What did you get, Andrew? Yeah. 1,900 about?
Yeah.
Good, good. Do I need to write this down? No.
Just a quick question. The negative sign is insignificant.
Not insignificant. You probably typed it in backwards. It's minus 10.
I did not type it at all.
Oh, you wrote 9. 9 is correct. The sign is correct there. Yeah.
So they're looking for the two outside.
In this one it is. Yep. In this one it is. Okay. Good job. Now here's a harder one, which I probably will have to do, but I want you to try it. An electric heater has a power rating of 3 kilowatts and it's used to heat a room that is 10 by 10 by 5 meters. Not big enough. The room is at 10 Celsius and the desired temperature is 20 Celsius. Take density of air to be 1 kilogram per meter cubed. How long would it take for the room to reach the desired temperature? In other words, a bit like the example I did at the start with the tea. How long until you're at 20 Celsius?
Long enough.
Calculate. And then I'll do it.
See, we study Q equals MC degrees. And then we get to this. That's what I don't like about physics. But it's still fun.
But this is like, the reason for that is because you have to try to quickly make the problems realistic. So like, the reason you study this is not because you need to work out how long it takes to make tea, because no one cares about that. It's for like problems like this.
So the mass is 1 kilogram.
No.
No, you have to work out the mass.
Yeah, but the volume and the density are the same.
The
Oh, wait.
No, it's not.
Okay.
Calm yourself down, Faisal. Oh my goodness, just tone it down, please. I feel like Lee and Andrew here. No, they look a bit more awake now. Remember your answers in seconds. Who else has an answer? Is it right? This is why you make notes, Faisal. You want the heat capacity of air, is it? Got an answer? Can I give you the answer now? Guys, can I give you the answer now? Okay. Okay. Power equals, guys, come on. Power equals work over time. So what does time equal? Sounds about right, yeah. Work is the amount of heat you needed, and the power is, what was it? 3,000. This is MC delta theta over 3,000. Now, some of this stuff you know. Do you know the M? No. Do you know the C?
Yes.
The delta theta?
Yes. 10.
Oops, that's why.
So, the only thing left to find is the M. Well, we can get that by using this formula. So what does the M equal?
500 times 500.
What?
500.
No,
Times 100. No, times 500.
Oh, how are you calculating?
You're finding M, so you multiply the density.
Density is 1?
Density is 1.
Density is not 1. What?
Yes, it is.
Can you go back to the question?
Okay.
kg per meter cube.
Say the density of air to be
Yeah.
1.
Per meter cube. You have 50 meter cube.
So you multiply
1.
500 meter cube.
Yeah, you have 500 meter cube. So you have 500
Density.
kilograms.
Finding density. Density is stable no matter what the volume is.
Density of water is
Density of
doesn't change.
Density of 1 liter of water is the same as density of 500
gallon.
liters of water. Density.
Calm down. The volume is 500. The density is, no, the density is given to you. It can't be 500 and 1 at the same time. Its density is 1 kilogram.
That's the unit.
Yeah? Okay. Anyways, the volume is 500. Okay, so what does this work out as?
This is for what? Time.
Yes.
1686 seconds.
1687.
7. 87.
28 minutes. Very good. Very good. So, although this is a hard one, it wasn't that hard. Okay. Here's the last one, and I'll do it here for you. Yeah. A physics student is making a latte. He mixes 200 grams of hot milk at 27 Celsius to 50 grams of hot coffee at 80 Celsius. You can assume the coffee is like water. Estimate the final temperature of the delicious, warm, steamy latte.
What do we have to use?
Yesterday's lesson?
You're right, you will have to make me a latte to test if the answer is right. And I welcome you all to make me a latte.
Nice.
One per day, please.
Nice try. But I am not a young woman.
Definitely not. Otherwise you'd be one ugly woman. That'd be rough. Right, okay. So, how much milk do we have? 200 grams. What? What? 200 grams.
Such a bad imagination.
Keep it over there, please. The milk is 200 grams and the temperature is 27. And then the coffee, how much coffee did we have? I think I said 50 grams. And the temperature? 80. And then what you do is you mix the two together. Will the temperature be 27 at the end? No. Will it be 80? No. It'll be somewhere in between. So I know when you mix them together, they mix together, obviously. But in the picture, it's kind of useful to imagine them as separate still. But the only thing you know is the mass is still the same. The temperature of both will be the same. And the heat capacity you're given. So think about this. When you add these two together to make this, is this going to lose or gain?
Gain.
This will gain, it will become warmer, and this one here will lose. The conservation of energy states energy cannot be created nor destroyed. So it means the energy that is gained by this one comes at the expense of this one here. That is, the gain of this is equal to the loss of this. So, mc delta theta for the milk should equal mc delta theta for the coffee. No, because, well, let's write it in here. What's the mass of milk? The heat capacity of milk? Now, the milk starts at 27 and increases to x. So the change is what?
X minus 1.
And that should equal m c, and the water or coffee starts at 80 and decreases to x. So the change is 80 minus x. What type of equation is this? It's just a linear equation which can easily be solved, even by the weakest of math students. Yeah, the last thing I'll have you to do is solve it, and then once you get the answer, we'll wrap it up there. Okay, so I want everyone to solve this. I recommend, before you solve it, I recommend multiplying the 0.2 onto this to make it one number, and this onto this to make it one number. So then you just have one number times x minus 27 equals one number times 80 minus x. And then you should expand again.
What are we multiplying again? The heat loss?
The x, the final temperature. Yeah.
is the pen? The pen. The thing you keep on the table.
Guys, you got an answer? You got an answer?
Yes, but it seems wrong.
41.
Believe in yourself.
It's wrong.
What answer did you get?
88.9, that's not possible.
21.
No problem. Let's find out the right answer. I'm really disappointed that we all have different answers. Wait, your answer?
It's wrong.
What is it? What is it?
88.9.
Okay, yours? That's worse. 88.
41.2.
You?
I'm doing it now.
21.2.
Wow. You?
Extra math class.
41.2.
Okay.
Yeah, I got 42.
No one believes your lies, right? So 0.2 times 2850 times x minus 27 equals
0.05.
0.05 times 4181 times 18 minus x. Yes, yes. Calm down now, calm down. Right. Ready? Ready? We'll see who's right.
Wait,
No, no.
Wait, I didn't see it,
Roll credits and we're finished. So, I think that was the last one. No.
Homework.
Yeah, I'll leave, if you want to watch the YouTube, well, I don't think I'll have time to upload it today. If you want to try this one,
Take a picture of the right now. You have 10 seconds.
yeah,
9,
and
8, 7.
wait, just be quiet. This question here, I'll explain it to you. Listen, a 10 gram,
Oh, this looks nice.
maybe you just want to take a picture, but a 10 gram bullet hits the wall at 100 meters per second. How much warmer will it be when it hits the wall? Because it warms up when it hits the wall. Like in the movies, when you blow someone's head off, smoke comes out. This is because the bullet gets really hot.
Because the bullet hits me, the bullet will explode, not me.
How much?
Yeah, temperature, yeah.
I sent a picture on the group.
Guys, so in the next class, what we'll do is I'll give you the answer to this last example, and then we'll do these together. It's only one question.
So we should do this for homework.
Yeah, do we do it for homework or?
Guys, you know what the deal is. You've been doing physics for like 12 weeks now.
Just the way you worded it sounds very different.
No, I would like you to do this for homework, but like I said, you're managing your own homework. So whether you do it or not, I'm still going to do it in the next class, because you still have to see the answer. So if everybody does it, I'll just give you the answers directly. If nobody does it, then we'll work on it in class.
Couldn't you scroll back to the
Question, we sent it on the group.
no, the answer and the
What was your answer?
what's wrong?
You go.
41.2.
What was your answer?
41.
Oh.